Okay, we are ready to start. So today we have Jordan Cotler, who will be telling us about isometric evolution in the zeta quantum gravity. And there's a dinner being organized. Okay, and what?
Yeah,
at 6.
Either of us.
They're leaving at 6, and please let them know if you're interested in going. Okay, thank you.
Great. Well, thank you so much for giving me the opportunity to speak, and it's been great to be here at IIS. So today I'm going to tell you about some work in collaboration with Christian Jensen that recently appeared. That's the one at the very top, as well as some work in progress. And some of the conceptual underpinnings of what I'm going to talk about today come from a work last year with Andy Strominger. So let me begin, there we go, by asking some questions. So the first question that I want to ask is, do the postulates of quantum mechanics survive in quantum gravity? So what do I mean by this? So our main tools for quantum gravity include the gravitational path integral and its Hamiltonian formulation, as well as string theory. And these each produce states and transition amplitudes. The parts of the formalisms of both gravitational path integral as well as string theory naturally have states and transition amplitudes which are produced by computations within them. However, unitarity is not guaranteed a priori in the path integral, and as such, it must be checked. So with that in mind, let's ask a second seemingly unrelated question, which is, so there are classical initial conditions in cosmology which lead to a crunch, which lead to the universe crunching at some finite time. The question is, what is their fate in quantum gravity? Now, there have been various ideas throughout the years proposed for how this works. So let me first draw a little cartoon. Suppose on some initial spatial slice that we prepare some initial conditions that I label by I, and then we evolve this. And as it evolves, space-time ends up ending in a crunch. So some proposals that people have said are that maybe these kinds of crunch states do not exist in bulk quantum gravity. So this is just a suggestion. I'm not going to attempt to justify this, but these are words that have been said. However, initial conditions that you might want to rule out of the bulk by virtue of them crunching or having some singular behavior correspond to perfectly reasonable asymptotic states in the de Sitter-S matrix. Namely, states which look perfectly fine from the view of asymptotics can lead to difficulties or problematic issues in the bulk at finite times. So one possible way out of this is if the bulk Hilbert space does not equal the asymptotic Hilbert space. We should regard this as just some impressionistic suggestion. We will attempt to make this precise in some concrete models later on. Another possibility is that maybe there exist asymptotic states, ones that crunch, which are projected out by de Sitter evolution. That somehow, when we evolve these initial states, they disappear. So these two questions taken together will bear some relation to one another. We need to understand what their answers might even look like, and to get beyond thinking about conceptual questions or heuristics, we need a framework for de Sitter quantum gravity in which we can actually perform computations, reliable computations, in which we can attempt to address what the answers to these questions can even look like in a precise way. So I'm going to consider in this talk two simple models, namely de Sitter Jackiw-Teitelboim gravity, as well as Einstein gravity with a positive cosmological constant in a Minisuperspace truncation in order to gain some intuition. Within these models, but in particular the context of de Sitter Jackiw-Teitelboim gravity, I'm going to provide a computational framework and explain what the rules are and how they comport with the usual rules by which we compute amplitudes in quantum gravity, and show you that there is a way in which these questions can be answered in these simple toy cases. And then I will speculate at the end as to what the more general story would be for higher dimensions and potentially for our own universe, if I get very speculative. So let me summarize for you what the main technical results are, which then I will spend the rest of the talk attempting to elucidate in detail. So in de Sitter Jackiw-Teitelboim gravity, the evolution from the bulk to the infinite future is isometric as opposed to unitary. So let me say what this means. So what this means is, here's a picture of global de Sitter in 1 + 1 dimensions. The spatial cross sections are circles. And we have a map from asymptotic states in the far past asymptotic states in the far future, where the evolution is governed by this S matrix, which I call U hat. And we can decompose this in a way which I will describe later into two pieces. One, which is a map from the asymptotic Hilbert space to some bulk Hilbert space by a map V dagger. And then a map from the bulk Hilbert space to the asymptotic Hilbert space, which is given by V. It is the composition of V dagger and V which gives rise to the de Sitter S matrix U. And what we will find is that this map from the bulk to the asymptotic boundary is not a unitary map, but an isometric map. So what do I mean by this? So will V dagger V is equal to the identity operator? It will be the case that V dagger, which is the combination that gives us the de Sitter S matrix, is in fact equal to a projector. That is, that the map U, which is given by composing V and V dagger in this direction, namely V dagger like this is not going to be unitary, but is rather going to be a projection onto a subspace of the asymptotic states of the Hilbert space. And the way that this will come to be is that the bulk Hilbert space and the asymptotic Hilbert spaces will be different from one another. So what will ultimately reconcile in due course the distinction between the bulk and asymptotic Hilbert spaces is the fact that the evolution between them is given by an isometry. Now, I will explain how these conclusions follow in a particular way from a path integral or a sum over smooth metrics. I will explain later what precisely I mean by this. Now, we will also find some initial suggestive evidence that this picture may be true in Einstein gravity, but I regard this as just very preliminary evidence because we're just going to look at a Minisuperspace truncation, which is of course not an approximation of Einstein gravity, but a truncation thereof, but it suggests some interesting ideas as to how the story may develop in higher dimensions. Yes?
Is V dagger supposed to represent semi-classical bulk evolution? Like when you say H bulk, is this like a semi-classical bulk? Or...
Let me return to that in a little bit because I'll define everything more precisely. So the talk is going to be divided into three parts. In the first part, I'll discuss de Sitter Jackiw-Teitelboim gravity. That will be the main meat of the talk. And then I will attempt to generalize some of the lessons in de Sitter Jackiw-Teitelboim gravity to the context of the Minisuperspace truncation, where we will see some little an inkling of how this may generalize to higher dimensions. And then finally, I'll conclude with a discussion in which I will make some speculative remarks about what the more general story might look like down the line. So let me begin with DS Jackiw-Teitelboim gravity. So I know we have many experts on Jackiw-Teitelboim gravity in the audience, so I will keep it rather brief. So de Sitter Jackiw-Teitelboim gravity was studied originally in a series of papers by people in this room, by Molly Sanitariachi and Yang, as well as by myself and Christian Jensen and Alex Maloney in 2019. And here is the action for JT gravity, in de Sitter JT gravity. Here we have a non-dynamical dilaton whose role in life is to localize us to metrics with constant curvature, namely r equals 2. We also have this important boundary term, and we have separately the term which is proportional to the Euler characteristic, which is just the integral of the ordinary curvature. And with this, let me write down some global DS2 geometries that you can get by solving the equations of motion, accompanying with a picture. So this is the profile of the dilaton. It interpolates between a negative value in the far past to a positive value in the far future, or the other way around, it depends on the sign of phi naught. And what the metrics look like is minus dt squared plus alpha squared cosh squared of t times dx squared, where x is a periodic variable. This corresponds to the spatial slices in de Sitter. And alpha is regarded as, that corresponds to the size of the bottleneck. But the circumference of the bottleneck in the very middle of these spacetimes is 2 pi times alpha. Now, this is, because it's a theory of low dimensional gravity, in fact, it has no propagating degrees of freedom in the bulk, but it does have boundary gravitons, which are captured by the physics of the Shortzian modes, and it has a moduli space. It has moduli space solutions. So let me now tell you what are the boundary conditions. What do we mean when we say this is an asymptotically de Sitter spacetime in this context? So the boundary conditions in the far future are as follows. it goes to minus dt squared plus e to the 2t plus some order 1 subleading term times dx squared. And then the dilaton goes to some, it's some function of x. It can be some function of x, so e to the phi of x plus t, as t goes to the far future. So these are the boundary conditions which we put in the far future, and if you put in some minus signs, you get the boundary conditions in the far past. And we'll discuss in more detail how we should think about the space of asymptotic states, but these are the boundary conditions that I will impose henceforth. Now, the key is that we would like to incorporate an arbitrary dilaton profile. We will be agnostic about this for the moment, but we will see that that once we account for diffeomorphisms properly, that many of the states that seemingly correspond to distinct dilaton profiles will be related to one another in the asymptotic Hilbert space, but I'll discuss this in a moment. So, so there's a natural way of decomposing this global de Sitter spacetime into two pieces given by these so-called trumpet factors. So those who are familiar with the trumpet that arises in Euclidean ADS Jackiw-Teitelboim gravity, this is the de Sitter analog of it. So we see that that for when alpha is not equal to, when alpha is non-integer, for general values of alpha, namely the bottleneck, this actually describes the upper part of the diagram. So let me erase the bottom part and put it in f of x. The f of x, these wiggles can be thought of as capturing the physics of the Schwarzschild modes of the boundary gravitons. These f satisfies the periodicity condition can be regarded for general alpha as an element of diff S1 mod v1. Of course, for alpha equals 1, if you're computing, for example, like the Harle state, then for alpha equals 1, it gets enhanced, it becomes diff S1 mod PSL2. So the basic picture that you should have in your head as to how we compute the global de Sitter amplitudes is that we want it to end in some state e to the phi labeled by the dilaton profile. And what we're going to do is we're going to glue together two different trumpets which have different dilaton configurations, one in the past, e to the phi tilde in the past, and one e to the phi in the future. And we're going to glue them together by integrating over the length of the bottleneck. This is the sense in which we are going to, integrate over smooth geometries is in the sense that alpha squared will be regarded as being greater than 0, so that there's not a cone point at the bottleneck. So this is a schematic for how we're going to compute these S matrix elements from the far past to the far future. So what are the ingredients that we need to flesh?
Question. Yeah,
yes.
On the previous slide, can you explain the integral over alpha squared again? What's happening there?
Well, the idea is that you take these two trumpets. This is also as you do in ordinary Jackiw-Teitelboim gravity in ADS, and you glue them together, and you glue them together with a particular fixed value of the circumference of the bottleneck. And what you do is that you integrate over all.
Oh, okay. Okay. And could you explain the justification for the boundary condition that you impose on the metric and the dilaton?
Well, at the level of the metric, I mean, these are natural asymptotically de Sitter boundary conditions for this problem. I mean, this is sort of, this emulates what things look like in higher dimensions. I mean, how do I say? This is supposed to match as well as possible with the ADS analysis. I mean, these look a lot like the ADS boundary conditions, like in the Euclidean case, but instead where we now furnish an arbitrary dilaton profile. So it's by analogy with the ADS case. Yeah.
I assume we have a boundary at like plus infinity, minus infinity. How are you defining it? It's like the surface of constant dilaton like in ADS or something?
Well, all I need to right. It's not necessarily a surface of constant. We'll come back later as to whether we should regard how we should think about the dilaton configurations. But all I mean is I'm defining the asymptotics by in this manner.
Without a sharp boundary, okay.
Yeah, without a sharp boundary.
Sorry. In principle, you could also have the metric to depend on x, but maybe I mean it's all related by difference probably, but you have the metric to depend also on x, but maybe the condition that the length is fixed, and probably you have the most general boundary condition you could write. What else?
That's true. I guess there's other ways there's other presentations of the asymptotically de boundary conditions. Let me consider this one for now, and we can consider the possibility of generalizations later, or maybe as you say, they're not actually generalizations at all because they're actually related, but it depends exactly what you want to write down. But let me write down this for now and proceed with this. So the four ingredients that we're going to need to flesh out our story are the asymptotic Hilbert space, H asymptotic. We're going to need the de Sitter S matrix, the map from the asymptotic Hilbert space in the past to the one in the future. We're going to need a definition of the bulk Hilbert space. And we're also going to need a bulk to asymptotic map V, which brings us from the bulk Hilbert space to the asymptotic Hilbert space. Now, in defining these objects, it's not enough when I give you a Hilbert space just to tell you some that it's spanned by a certain set of vectors or a certain set of basis elements. I need to also provide you the inner products on each Hilbert space. And the reason that this is important is that if I were to just hand you the S matrix elements, but not tell you what the normalization is on states in which I'm computing the matrix elements, we wouldn't necessarily know how to interpret it with regard to unitarity. Then in order to really understand whether something is unitary, we need to understand the S matrix elements calibrated by our definition of the norm on the states, namely by the inner product on the asymptotic states, with which we use to sandwich the de Sitter S matrix. So the ingredient of the inner product will be crucial for our story. So let me first talk about the asymptotic Hilbert space. And let me begin by saying that the putative Hilbert space in the far future, which we will refine, is the states which are labeled by e to the phi of x, by these arbitrary dilettante configurations. This is our putative Hilbert space, which we will prune in a moment after we have a better understanding of the inner product and of the diffeomorphism. So here's the picture that I want to draw to you to motivate the computation, which I will describe next. So the picture of how we should compute the inner product on asymptotic states is as follows. So think about just an ordinary, for the moment, an ordinary quantum mechanical system in which I have an initial state and I have a final state with some amount of time evolution between them. And I take the limit as the amount of time evolution between them tends to 0. As that amount of time evolution tends to 0, that will just compute the inner product between the two states. It'll just be one state sandwiched against another with no evolution in between. The picture that we then want to have is that we set up a boundary in the far future in which the dilettante has configuration e to the phi 1. And then we set up another surface a little bit in the past in which it has a configuration e to the phi 2. And what we would like to do is to take the limit that both of these tend to the far future towards t goes to infinity and also tend towards one another so that the surfaces coincide. That's the kind of picture that we would like to substantiate by writing down an equation. So let me propose a way of interpreting this picture in an actual set of equations. If you take the metric in the far future after doing a shift of the time coordinate, and you expand it out in the far future, what you find is that these global de Sitter metrics, you find that there is this leading exponential growing term, which is the expansion of the de Sitter space. And now there is this sub-leading order 1 contribution. Now, in the global de Sitter geometry, this alpha squared was previously interpreted, or the alpha was related to the length of the bottleneck. But here we see that when we expand the metric in the far future, that in the limit, that t is taken to infinity first, that t is taken greater than everything else. That now the sign of alpha squared as a modulus that we need to integrate over becomes unrestricted. Now here, if we forget the original interpretation of alpha squared and just look at this as a subleading constant, in the asymptotic expansion of the metric, there's nothing that dictates that this parameter, that 1/2 alpha squared, should be positive or that it should be negative. It can be negative because the first term is really, really large. So having a negative second term, so long as it doesn't dwarf the size of the first term, is unproblematic. This suggests then that the inner product should be given by soldering together two trumpets together with a complex conjugate on one of them to account for orientations. But now where we integrate over all values of alpha squared, we integrate from alpha squared from -infinity to infinity. And let's see what we get by doing this. So when we do this, the answer that you find, let me unpack this, box this as a key equation. So we get this answer for the inner product. So what are these capital phi's? What is this s? What does this mean? So here, 1 over big phi is this 0 mode. It's this 1/2 pi integral from 0 to 2 pi of e to the -phi around the circle. even though it's not really a zero mode of little phi, I'm going to refer to this object big phi as the zero mode, okay, just for convenience. And then we have this other object, which is a functional of this of the dilettante configuration, which is also an integral along the circle of e to the little phi times phi prime squared downstairs. So what we find is that there is a delta function, there's this prefactor which depends on the zero modes, and there's these exponential terms. So what do we make of this? So the first observation is that this inner product has null states. Here is an example of what the null states look like. If you take a little phi 1 and a little phi 2, which have the same zero mode, if big phi 1 equals big phi 2, then you can check that this state actually is a null state with respect to this inner product. And I'll explain what the physical interpretation of this is in a moment. But to establish the Hilbert space, we would like to, if we have a putative Hilbert space and we have null states, we should quotient out by the null states. In so doing, quotienting out by the null space identifies all of the dilettante configurations e to the phi that have the same zero mode. It turns out that the null states are precisely, that when we quotient out by the null states, it precisely identifies all of these e to the phi configurations with the big phi that corresponds to the zero mode according to this expression. I'll give you 1 second, I'll mention. So then the putative asymptotic Hilbert space is the span over these states labeled by big phi, where phi can take any real value. Yes?
Was it important to go from minus infinity to infinity to get these null states, or?
Yes. So what do the null states mean? What's the physical picture? So this is the result of a computation, but should we have expected these null states? What's going on here? So there is a physical reason for these null states, which is that there's a diff S1 family of large diffeomorphisms which preserve the asymptotic metric, but do not preserve the profile of the dilettante in the far future. So in particular, there are these diffeomorphisms which change the profile of the dilettante, and as such, they change the profile of the dilettante, but they preserve the zero mode. As such, on the basis of this information, what you would a priori expect is that you should expect to identify an e to the phi and an e to the phi tilde if they have the same zero mode. That's what you would suggest by virtue of them being related by these large diffeomorphisms which preserve the asymptotic metric, but not the dilettante. But again, they do preserve the zero mode. So in fact, this expectation, the idea that these two would be related to each other, is borne out by the structure of the null states according to this inner product. So in fact, this is what we found. This expectation is realized by the computation of the inner product that I have presented.
So if is phi can phi be complex? Because if phi is real, how do you get a real large phi? Small phi, if small phi is real, it seems large phi should always be positive.
And I'm not sure I understand the question. So I'm assuming the phi's are real. We're going to consider real values of the dilettante is going to be a real function. The metrics are
So
also
you have large phi in your slide, large phi, and you have small phi, right?
large phi and small phi, yes.
Yeah, so small phi, is it real?
Yeah.
Then large phi, as you've defined it, it seems like it should be positive.
Oh, sorry. There's also an issue of right. There's also a matter of there are signs also that I good. There's something that I have swept under the rug here, which is this issue of orientation. There is actually there's a factor that I dropped which corresponds to an overall sign. Let me I can write the equation on the board in a bit, but that's a good catch. Let's come back to this in a moment. Good point. So,
I have a related question, sorry.
Yeah.
Could you go back to the metric? Is there an interpretation of capital phi as a length of some curve in your spacetime?
good. So I can't offer you a good interpretation of big phi, but I can offer you a good interpretation shortly of its Fourier conjugate. It turns out that its Fourier conjugate will be related to the size of the bottleneck.
I was expecting you to tell me that the capital phi or capital phi inverse was the size of the bottleneck, but that's not.
That's not the case, but its Fourier conjugate is. But I'll show you that explicitly in a moment. So let's
Fourier conjugate or Laplace conjugate?
Fourier.
What is Fourier conjugate of length?
Well, what is the Fourier conjugate of length? Well, all I mean simply is that if I take the, I'll show you, I'll discuss this point in detail actually, is that if you look at the asymptotic states that are spanned by phi, and I just look at their Fourier transforms, and I look at what geometries those correspond to in the bulk, the ones that have fixed Fourier conjugate to phi, which I'll call P, those are the ones that are going to correspond to a bottleneck of size P. That's the statement which I made. I'll elaborate on that in a moment, but that's what I'm trying to say. In any case, for these phi 1 and phi 2, it's convenient to redefine them by dividing by the square root of phi and to strip off these factors in front of the delta function. So I will do that here. So now let me talk about the de Sitter S matrix.
Can I ask you one question? In the diffeomorphisms that you used before to make that constant, is it obvious that it's allowed, or you said it doesn't change the metric, but can it change the periodicity on the, like X has a certain periodicity, but maybe you do that transformation, it has a different one?
No, it doesn't mess with the periodicity.
Oh, okay.
So now we would like to compute these S matrix elements from phi 1 to from phi 2 in the past to phi 1 in the future. And as I explained before, if we would like to do a path integral over smooth geometries, we should solder together these two trumpets where we integrate over positive alpha squared. And when we do this, this is the answer that we find when you perform this integral. And this looks much nicer in Fourier space. Your Fourier transform glands may be salivating or something when you see this. If you do if you look at a conjugate basis, this is what I mean by a P basis, something which is conjugate to phi defined in this manner. What you find is that in the P basis, this object is of course just the Heaviside step function, which projects you onto positive momentum. So it's just theta of P times, it's just something which projects you onto positive P states. Well, I'll offer an interpretation of this in a moment, a bulk interpretation of what this means. But importantly, this object is not unitary. This is not a unitary, it's something which projects us onto a subspace of the asymptotic Hilbert space. So we have two of our ingredients.
I have a question. These states, do they satisfy all the standard constraints like Wheeler-DeWitt, momentum constraint, etc., or not?
They should, yes. I mean, they're usually when I think about Wheeler-DeWitt, so I think that it's easier to talk about those things in the context of the bulk Hilbert space. The Wheeler-DeWitt picture is sort of most natural in the bulk at finite times, but these states are, okay, well, maybe I should ask, I'm not sure exactly what you mean by that for the asymptotic Hilbert space, but these correspond to valid boundary conditions, which I can put in the path integral. And as such, I would like to identify them with boundary states modulo these null states. But maybe I don't quite understand what you mean by satisfying the constraints.
It's a state in some Hilbert space, and we might or might not want to impose the physical state conditions. That's what I thought the Wheeler-DeWitt and the momentum, all the constraints coming from diffeomorphism. So there's a question.
I am opposing all of the constraints that come from diffeomorphism. That is true. The kind of avatar of that in this computation is the fact that the only physical states are those which are labeled by constant phis. That's all that's left after accounting for the diffeomorphisms.
It's not viewing these states as functions of the metric and phi. So if you introduce a function of a metric and phi, then you have the Wheeler-DeWitt equation.
Yes.
So the answer is yes. So these states satisfy all the constraints.
Yeah. So it's good to work so let me work in the P basis. So this is what the asymptotic Hilbert space is in the P basis as opposed to the phi basis. So now let me talk about the bulk Hilbert space and attempt to define the bulk Hilbert space. So a bulk analysis will help explain the presence of this projector. So if we gauge fix, if we have minus dt squared, that we gauge fix in the sense that we mandate that the coefficient of the dt squared term is -1 and that there's no cross terms between t and x, then we just have this warp factor that sits in front of the dx squared. And if we write now the JT action in this, with this gauge fixing, if I define a curly Q by 5, the dilettante over A dot, and I define P by A squared minus A dot squared, then in those variables, the JT bulk action takes a simple form. It looks just like Q times P dot. Okay. And this presents us with two obvious or particularly obvious options for the boundary conditions. The first is that you can fix Q as t goes to infinity, preparing some state Q of x, where note that as t goes to infinity, you're essentially just fixing the dilettante profile. Or the other option is you can fix P as t goes to plus or minus infinity, preparing some state P of x. We will opt for the second possibility. This will be nicer from our point of view. So, okay, so the putative bulk Hilbert space is the span of these curly P of x's. And recall, though, that there is a relation between P and the warp factor. And in particular, if we look at the solutions to the equations of motion, non-singularity of the bulk geometry requires these C plus or minus coefficients to be non-zero. In particular, we know that P of x, this big P of x, can be straightened out with a large diffeomorphism by a similar kind of analysis than what I explained before, that all of these big P of x's can be straightened out to have a constant representative, so that we should similarly identify these big P of x's with a representative of constant P. Now, the question now is which value should we permit for this big P? Which is it the span of P in all of the real numbers? So to gain some understanding of this, it's instructive to reconstruct the bulk metric in terms of P. So when we do so, we find that for P greater than 0, we recover just the ordinary bouncing cosmology, where we have a cosh squared of T, and then P, the big calligraphic P is the thing that lies in front of the cosh squared. For P less than 0, we find that the absolute value of P sits in front of a sin squared of T, which corresponds to a crunch because the warp factor goes to 0 at T equals 0. There's a conical singularity. So something which is tempting to do, which I will attempt to offer motivation for, is that because of the fact that in our when we compute the S matrix elements, we are integrating only over smooth geometries, namely ones for which the bottleneck is greater than 0. What we would like to do is that if we only want the bouncing cosmologies that correspond to non-singular ones, I simply think we keep the ones which are P greater than 0 and not the ones that are P less than 0. That is consistent, I suggest, with our prescription of summing over only bulk smooth geometries. So those are the ones which we are keeping. And you can see from this formula there is an identification of what between P and what I was calling alpha squared. So the bulk Hilbert space then would be the span over these big P's for P greater than 0, corresponding to bounce cosmologies, which is like L2 of R greater than 0. And again, the P greater than 0 is again due to the restriction to smooth geometries without the compound.
So you're just deciding to keep only P greater than 0, or is it an actual? I'm sorry if I didn't follow, but is this a choice that we're making, or is this something that is? So let me make this point, then I will have 2 points in favor of why I think it is a justified choice. Okay, but it's a choice, so it is a choice.
Well, I would like to. That is the most conservative way of putting it, but I could say I don't think it's a choice, but I think it's not a choice. I think that's the self-consistent thing to do. Okay, so I'll say it's not a choice. We have to do it, but with some caveats. So since P is conserved, it's actually conserved by the bulk dynamics. The bulk evolution acts trivially. In other words, that if you just evolve for any amount of finite time, just because our action was QP dot, P at one time is P at any later time. So that is that on these P states, the bulk evolution is trivial. Nothing happens. This is kind of like some avatar of this hack-fat. Once you impose all of the Hamiltonian, once you impose all of the constraints in the bulk, the evolution looks like the identity, it looks trivial. So the things that I would say are in favor of why we should restrict to positive P is one, that in all of the other computations, particularly the computations where we're looking at the the norm on asymptotic states, and we're looking also specifically at the S matrix elements, we're integrating only over those geometries which are smooth, which do not have cone points. Because if we do have cone points, a priori, we should soak that up with some defect in the JT model, which I'm not assuming we have. The other, I think, point in favor of that prescription or that choice is the fact that the bulk evolution is trivial. Like it's just, once we've done the gauge fixing, it's just the action is QP dot. So P's now are mapped to P's later, nothing changes. So what's nice about saying P is greater than 0 is that you don't run into a potential issue, because if you had a negative P and it was just evolved by the identity for all time and it didn't, it somehow gets, it would be contradictory that it would be mapped out of the S matrix evolution. That a negative P for any finite time, nothing happens to it, but suddenly when you go to the S matrix evolution, that is projecting out P's. I think that the choice which makes the picture most consistent, especially in light of something which the last ingredient, which I will tell you in a few moments, is to make P greater, this big P to be greater than 0. That will actually make the story cohere very nicely and seems to me like a self-consistent choice. So, and again, since we have P equals alpha squared, we can think of these big P's as states of fixed bottleneck size. Now,
it kind of dimensions the sign of P is just the choice of gates. You have it's a special curvature, negative special curvature. So this you find a singularity in the metric, but it is not physical singularity. The curvature is not singular.
It is in these metrics, you can compute it.
But here it's 2 dimensions, that's why.
Let me not yet comment on the higher dimensional picture. Things are a bit different in higher dimensions, but let me comment on that later. So the last ingredient that we need is the bulk to asymptotic map V, which brings us from the bulk to the asymptotic future. And this will tie the story together. So the bulk to asymptotic map is our good friend from before, this JT trumpet. It is this map which takes us from the bottleneck to the far future, from the bulk Hilbert space as I have defined it to the asymptotic Hilbert space. And the matrix elements simply relate this little p that we were discussing from before, which is the Fourier transform of the states in the far future, to this big P, which are the states which are defined naturally in the bulk. So we can think about this, hold on a second, as a change of basis matrix from the big P's down here to the little p's up there. So that in this sense, they are canonically identified when both of them are greater than 0. In other words, the p's down here are greater than or equal to 0. These p's here can range anywhere on the real line. So what this object does is it embeds these positive p's into a subset of these p's, namely those which are positive. Let me just finish the thought. So what this then is that V dagger V is simply then the identity map or on the bulk Hilbert space. But VV dagger then ends up being the S matrix, which is a projector onto positive little p. So as such, we can think about the trumpet as instantiating an isometry from the bulk Hilbert space to the boundary Hilbert space. Yes.
Yeah, it seems that the geometries where it crunches, it's a little bit like a double cone type geometry. Is that correct?
That's right.
Is there a way of, I mean, we know how to regulate the double cone. Is there a way of regulating this particular crunching geometry so as to still include them? Is there, or do you think there's no way of doing that?
So I think that there is not a self-consistent way of doing that within the context of this analysis. I'll present you a piece of evidence for it that's indirect in a little bit, and let me point it out. There's another piece of data that we have to suggest that this projector is really should really be there. But let me get back to that in a moment. That's a good question. But as it stands, these are the different ingredients in the story. We have the asymptotic Hilbert space, we have the de Sitter S matrix, we have the bulk Hilbert space, and we have the bulk to asymptotic map. And these all come together to present the following picture of what's going on. So let me summarize. The bulk and asymptotic Hilbert spaces in this picture are unequal to one another. The bulk Hilbert space does not equal the asymptotic Hilbert space. But this is reconciled by virtue of the fact that the de Sitter GTS matrix is not unitary, that it is a projector onto those states with positive P, which correspond to bulk geometries which bounce as opposed to crunch. However, we still have unitarity within a code subspace if I may use those words, of non-crunching states. Namely, the states with positive P, they just evolve on their merry way. They don't get projected out. Nothing happens to them. So if you are in the subspace of non-crunching states, then nothing happens to you. You just keep on evolving. It's only when you prepare a state in the asymptotic Hilbert space, which corresponds to a crunch, that you end up getting projected out. And moreover, this bulk to asymptotic map is an isometry. V dagger V is the identity in the bulk Hilbert space, as I have defined it. And VV dagger gives you the S matrix, which is actually a projector onto positive P. So let me make a few asides, one of which will address one of the questions provide some data towards this question that you asked about I epsilon, the form of the contour. Let's think about the Harle-Hawking state. So so here's a picture of the Harle-Hawking state that we start with Euclidean cap and then we evolve it using Lorentzian evolution into the far future. So in de Sitter Jackiw-Teitelboim gravity, we can compute the Harle-Hawking state. There's a computation you could use to compute it. Various people have done it. The picture that I would like to give to it, which I will attempt to justify, is that we have a cap state, a state of Euclidean cap that lives at in the bulk Hilbert space, which we evolve to the far future using the isometry V. Now, we can obtain then a bulk state by applying V dagger to both sides, by basically gluing on a trumpet in the other way, performing an integration. And this brings us back from the Harle-Hawking state down to the cap state in bulk. And when you get this, okay, so there it is. So I'll do it again. So it evolves down to the cap. And what you find in terms of these big P states in the bulk is that you get delta prime of big P minus 1. It is a non-normalizable state. This is consistent, so it's not normalizable, I should say, but it's still localized at a particular length of the bottleneck. And P equals alpha squared equals 1, namely the circumference of the bottleneck is 2 pi. So that makes sense. At least that feature of it makes sense.
Sorry, can I ask a question? So
Yes.
the empty set that's by definition this cap state,
That's right.
and that's a Euclidean path integral.
That's right.
So should one include other topologies?
Yeah, so at the moment I'm just restricting to the to genus 0. But so
If you include a sum over topologies, you're going to get another parameter and a modified state.
Yes, and the modified inner product.
Okay, thanks.
Sure. So I just want to observe that the fact that this is a non-normalizable state is consistent with the fact that the sphere partition function in J2 gravity is divergent. This is something that was computed by Mahajan, Stanford, and Yang. So the other thing that I would like to mention is that let me suggest another picture, which is if you take the Harle-Hawking state and you think about it as this, this cap with V acting on it, what happens if you look at the inner product? You glue two of the things together along the asymptotic boundary. What happens? So if we look at the Harle-Hawking state sandwiched against itself, this is a cap V dagger V cap. The V dagger V is the identity, so that cancels out. So if we look at this picture, it contracts down to just a sphere. So something that you might expect, or that this picture would suggest to you, is that the appropriate norm of the Harle-Hawking state would be the sphere partition function. Say to one loop, this is an interesting, at a tree level, this is not a particularly interesting statement, but at one loop, it could be an interesting statement. So something that we are currently trying to understand, which we're in the middle of with Harvey and Jensen, is to test whether this works to one loop in 3+1 dimensions as well as 2+1 dimensions, something that we are in the midst of. But something that it crucially involves, I should mention, is that in the same way that in the JT computation, when we computed the norm on asymptotic states, we found that there was this parameter alpha squared, which was freed up to be negative by the fact that we were looking at really large times first. And then we integrated alpha squared from -infinity to infinity. There's a similar kind of thing which happens when you compute the norms on asymptotic states even in higher dimensions. There are combinations of parameters that would a priori seem like they should be positive, but then when you expand them in the far future, because they are subleading to some term which blows up as t goes to infinity, you actually have to integrate over all of their values. That was the prescription we're using, and we don't yet know what the result of the computation will be. So let me present another piece of evidence about where this theta of P comes from.
So good question about the previous slide. So I did the test. So you're computing the Cotler-Hawking wave function at some very late time, and then taking some inner product and checking whether that's exactly the.
So the usual Harle-Hawking
sphere
state,
without-
as we think about it, is just the sphere. So you have to deform it. You have to look at an arbitrary metric on the topological sphere. So you can think about that as you can imagine that you can parameterize the deformations deforming it via some stress tensor. It just turns out that in so doing, the computation of the inner product actually has a saddle point approximation with some kind of complicated one loop effects that one has to account for. So it's not just the ordinary Harle-Hawking state on the sphere. You actually have to deform the metric and look at deformations.
We produce the state by doing half of the cup. When we do this inner product, we just get the function of the whole sphere naively. So. Sure.
Well, there's a question of what is the, oh, sorry, maybe I didn't understand. Okay, so the other piece of data that we have is that the de Sitter S matrix elements can be reproduced with the matrix model. But I'm only going to focus on the case of, well, I'm not going to think about higher genus. The higher genus story is actually kind of, that's another story that is actually has some open questions. So this is similar to these computations, very similar to these computations of Schaefer and Stanford in the Euclidean anti-de Sitter case. There's some double scale matrix model where matrices are taken large and you have a particular density of states where you're zooming in on the edge. And it turns out that there is, if you follow by analogy with what Schaefer and Stanford did, then you find that there are these objects, which I'll call half resolvents, trace of square root of 2 over minus IH minus P, that correspond to preparing these normalized P states in the asymptotic far past or the asymptotic far future, depending on the sign of I. And when you compute this correlator, in the matrix model, you look at the connected contribution, look at genus 0, that's the thing that would naturally correspond to the global de Sitter calculation, you get this state of P times delta of P minus P prime. So that is, it turns out that this quantity is none other than the spectral form factor in disguise. This is the universal connected part of the spectral form factor. Let me maybe write out one other equation to be slightly suggestive. So usually in, for example, the analysis of Schaefer and Stanford, they consider this quantity, which at genus 0, or the connected piece looks like this. Okay. So let me just suggest to you that the similarity between this and the theta function is that there's these factors of square root on the top. Recall earlier in the talk when we were working with these big phi states and there's these square roots that appear in the definition of the inner product. That is, when you normalize the states, it essentially corresponds to stripping off the square roots. Then what happens is that you just have 1 over beta 1 plus beta 2. And the appropriate kind of continuation of that gives the de Sitter answer is where you take one of the betas to I phi and the other to minus I phi prime. And that gives you then the Fourier representation of the step function. So this is the sense in which this universal quantity in random matrix theory, this spectral form factor, actually really encodes the physics of this projector. It just turns out that these square root resolvents are just a convenient way of working directly with the normalized states of fixed boundary momentum, this fixed little p. I think this is at least suggestive that there is something that has gone right about this computation producing this step function, that somehow this universal thing in the matrix model knows about the step function in this way. I think this is a bit mysterious as to why this is. Okay, but the point is this is universal in double-scaled random matrix theory with some additional assumptions. So let me speak a little bit about Minisuperspace. This is an attempt to kind of calibrate what the higher dimensional setting might look like. So we're going to consider a Minisuperspace truncation because we want to build evidence for similar mechanisms in higher dimensional gravity, in particular Einstein gravity. So let's consider Einstein gravity with a temporal gauge fixing. So here is the Einstein-Hilbert action, and we're going to consider this gauge fixing in which we have just a nice form for the TT and TI components. So this is like what we were doing before. And I will assume that the cosmological constant, I'll set the de Sitter length scale to be equal to 1. So this is just d times d minus 1 over 2. So the L that usually sits downstairs is going to be 1. And then we have this Lagrange multiplier, which enforces the gauge fixing. So the mini superspace truncation is just to look at metrics of this form where we only have work factors in front of the dt squared and the a sphere, spatial sphere, and then we just assume that everything is a function of time, including the Lagrange multiplier. So this is a brutal. This is not really an approximation; it's really an amputation. There's nothing approximate. People call it the mini superspace approximation. It's really just a truncation. So we shouldn't. This is sort of. This is just to see what's going on, but we should not trust that many features of this analysis will fully generalize to the full Einstein-Hilbert action. So if we do some change of variables, I define these x and y operators by e to the at and e to the d over 2 b of t, and then just redefine the constants in front of the Lagrange multiplier. This is the mini superspace action that you then get as a result. Here we see that we'll explore what this means in a moment, but it looks, at least the y components look kind of like a particle. If we have this y dot squared, this kinetic type term, and it looks like a particle in a funky potential, which is actually an inverted potential. So what's going on here? Well, this is better understood by looking at the equations of motion. If we vary lambda, this Lagrange multiplier, this sets x equal to 1. If we then vary y and then use the fact that x equals 1, then we get y double dot equals minus v of y. This just looks like an ordinary particle, this is just Newton's equations. And then if we vary x and set x equal to 1, then we find that lambda is forced to equal 1/2 y dot squared plus v of y. So by comparing the second set of the second equation and the third equation, we see that lambda is just the energy that is associated with the dynamics of y. As such, let me relabel lambda suggestively as E because it's really just the energy, okay?
Normally, if we hadn't introduced lambda, we would get that E0, right? The Hamiltonian constraint would be the
yes
motion for x.
That's right.
So I think this procedure of putting the constraint in the action is like choosing a gauge and then not varying over some of the variables. So that's why you're missing some equations.
That's right. Yes. So let me speak more to that in a moment, but this is I'll have something to say about that in a moment.
But there's supposed to be ghosts here as well, because we fixed a gauge, or maybe it doesn't show up at this point.
At the level of the equations of motion, on a shell, it's not going to matter. So the usual thing that we do is that we set E equal to 0, as Fawn was suggesting, that this is the ordinary Hamiltonian constraint. So this is the usual Hamiltonian constraint. But by virtue of having introduced this temporal gauge fixing, we are now allowing for the possibility that E can actually take on any value. And these kinds of solutions are called lambda solutions, and they can be viewed as types of constraint saddles. So let me unpack that for a moment. This is sort of a lower dimensional avatar of these constrained saddles, a particular kind that are called lambda solutions. So the idea is this. Usually in gauge theory or in gravity, as an example of, in particular we're interested in gravity, when we impose a gauge fixing condition, this introduces new terms into the action, namely lambda times, Lagrange multiplier times some gauge fixing constraint. There's also Jacobi. So here we're considering some temporal gauge fixing in which we've instantiated this in the Einstein's equation. Usually when we look for saddles in which Lagrange multiplier is set equal to 0, meaning that the solutions are just the solutions to the ordinary equations of motion, namely the equations of motion that would just be the ordinary Einstein's equations. But when you have this additional gauge fixing term, you are, at least at the semi-classical level, you are allowed to pick solutions in which lambda is not equal to 0. That is, in the language of constraint saddles or constraint instantons, the gauge fixing constraint is playing the role of the constraint instantons. I can say more about that, but that's what's going on at a high level.
Can you remind us how this coordinate y, so you end up just with y. Can you remind us its geometric interpretation?
Yes. So y here is related to the warp factor in front of the sphere. Y is just the is like the size of the sphere as a function of time. The thing in front of the sphere.
Is it like the length or the log of the length?
Sorry, the thing in front of the sphere. So let me go back one slide just to show you. Sorry. So y is like, so e to the 2b is the thing which is in front of the sphere. And y is e to the d over, it's just a power of that. E to the d.
So if I compare that with d equals 2, and I integrate out lambda, so x is 1, then I get a kinetic term, the y dot square. But then I would have expected I would have expected the potential to be proportional to the power of the length or the area. So that's correct. But the measure I would have expected is not y dot square in the kinetic term, but y dot over y quantity square.
And you have two terms because you have the curvature and the cosmological constant, right?
That's right. Okay, maybe we can address this later. I'm not sure I fully understand the expectation of. Okay. So anyway, so we can think about different values of E. And in fact, semi-classically, we can label, so if we label the states by different E's, by just thinking, but I don't really mean by quantizing, I just mean by looking at the space of solutions, that the one parameter that we can vary is this E, and these constraint saddle type solutions. That if we look at 3 + 1 at what the shape of the potential is, we see that that if E is below the maximum of the potential, then this corresponds to bounce solutions, whereas if it's above the maximum of the potential, it corresponds to crunches because V can reach 0 size. So we see that there's non-singular geometries for E less than V max, and as such, that it is natural to guess that in this mini superspace sense of the bulk Hilbert space, is a span over these states labeled by E, or the non-singular ones are the states spanned by the ones labeled by E for E less than V max. So I just want to show that even in kind of this cartoonish version of the mini superspace approximation, if you only wanted to keep non-singular geometries, that you still end up having something like these states where it ranges from from minus infinity to V max corresponds to the bounds, and then for V max for E greater than V max, you get these crunch geometries. This is just some picture about what the mini superspace suggests. But
this looks like the mini superspace of an FRW where you also add matter, right? If you add too much matter, then it collapses. I think your treatment is probably analogous to.
That's right.
Similar.
The constraints. The constraint is essentially playing the role of a TT stress tensor. So let me make a quick comment on Euclidean ADS wormholes, and then I'll make some final remarks before concluding, which is that these Lorentzian de Sitter constraint saddles connect to another subject, namely Euclidean anti-de Sitter constraint saddles. So let me just make a quick comment, which is that maybe I won't go too much into this, but there's been a lot of fruitful debate and discussion about the role of ADS Euclidean wormholes in higher dimensional gravity, in particular in its relation to ADS CFT. I want to observe that these constraint saddles in the Euclidean setting are not unrelated to the ones in the de Sitter setting. They're actually, in some cases, there's a very tight relationship between one and the other. I just want to observe that these two subjects are connected with one another in a certain way. In particular, these constraint saddles also come in families labeled by an energy, which is related to the size of the bottleneck. And these constraint saddles in the Euclidean ADS setting only exist for these E's above a certain threshold, which is kind of analogous with what's happening with the bottleneck in the de Sitter case. I just wanted to mention this as a bit of intuition or just a potential point of connection for people in the audience who think about this. So let me end now with some summary and then some speculative remarks. So the thing that we see, at least in this toy model, is that the S matrix need not be unitary in quantum gravity. At least what we have seen is that in this toy model, that it can be a projector, namely Jackiw-Teitelboim gravity. The bulk and asymptotic Hilbert spaces need not match, in our computations. These crunching initial conditions live in an asymptotic Hilbert space, but not in the code subspace of bulk states, which correspond to non-crunch states. Moreover, I think that the conceptual lesson of this might be that complete knowledge of bulk physics, even on arbitrarily large timescales, is not enough to deduce the de Sitter S matrix. Said in a different way, when we look at these bulk states and we look at any amount of time evolution of the bulk states, it's just the identity, nothing happens to them. And you wouldn't know by just looking at the bulk states at finite time, what is it that the S matrix, you wouldn't be able to deduce this projector, which is produced by the S matrix. So there is, in other words, that because of the fact that the bulk and asymptotic Hilbert spaces are distinct from one another, you have to bridge that gap using a non-unitary S matrix. So in our examples, we found that evolution is trivial within a code subspace, and the breakdown of unitarity is invisible in perturbation theory and only rises non-perturbatively by these integrals over these soldered Lorentzian JT trumpets. So let me conclude some comments and speculations about, do these lessons persist in greater than 2 + 1 dimensions? Now, notice that I haven't discussed 2 + 1 dimensions. I've only discussed 1 + 1 dimensions, the context of JT gravity. But there's reason to believe, and in fact, work in progress, that one can actually formulate similar results in the context of pure 3D gravity by a careful treatment of the gravitational path integral, at least for these global de Sitter geometries. So the Minisuperspace analysis is promising, but there's an essential kind of conceptual question in making any sense of this in any realistic context, which is the restriction to a sum over smooth geometries realized in UV completions of de Sitter quantum gravity, such as in string theory, insofar as they exist in a reasonable. So for instance, maybe certain singular metrics that are sensible in string theory ought to be included in the low energy theory, that we really should, sum over certain singular geometries. That seems like a logical possibility. So I think a useful toy model, which might be interesting to explore in this vein, is de Sitter JT coupled to defects. The defects now allow for the possibility of soaking up the curvature of the crunch. But in certain ways of incorporating the defects can only take on certain values. And as such, the bulk Hilbert space would encode the spectrum of viable geometric configurations in which the universe can crunch. It wouldn't just be P greater than 0, but it would be certain. It would also there would also be these isolated states P less than 0, corresponding to the values of the defects that can soak up the curvature. So in other words, the picture that I think might be true even in kind of a higher dimensional setting, for which this is just a toy model proxy for, is that maybe there are certain kinds of brain-like, there are certain things which furnish crunches, certain objects on which the universe can begin or end, and that somehow these objects are encoded in the bulk Hilbert space in some way. You can't kind of crunch just in any way, or you can't have a Big Bang in just any possible way. There's only sort of certain possibilities for it, and that these possibilities are encoded in the bulk Hilbert space in some manner. That's a very impressionistic remark. You can also think about gravity coupled to matter, and it would be interesting to understand also connections to black holes and final state projection, which this seems aligned with. So let me conclude by, last slide, is that we expect the true Hilbert space of de Sitter quantum gravity to be drastically smaller than indicated by its semi-classical description. In fact, what I would venture is that there's a belief that the bulk Hilbert space of de Sitter quantum gravity is even finite dimensional, as suggested, for example, by applying the holographic principle to the given computation of the horizon entropy and the static damage, for example. However, I think that so as I said, holographic argument suggests it's non-perturbatively finite. But nonetheless, it still may be the case that even if the bulk Hilbert space is non-perturbatively finite, that the boundary Hilbert space could still be infinite dimensional or still be much larger. I think that probably is the kernel of an idea that may survive in whatever the ultimate version of our understanding is. And I think our findings are a first baby step in this direction, where we can already see the pruning of bulk Hilbert space in the low energy effective description. That this points, however feebly, towards that direction. And with that, yeah, thank you so much for your attention.
Make sure I understand what the F matrix was. So they're the states that don't crunch,
Yes.
just sail through, and the ones that do crunch go nowhere.
That's right.
Okay. So the F matrix is 1. I mean, there is something that just acts on the states that sail through where it's just 1.
That's right. And in a certain
Why don't you just talk about that then? Why don't we just talk about that unitary, very nice unitary operator?
Just because there's a natural, because the boundary conditions naturally give us states which have non-zero norm, which are viable boundary states which we could prepare in the path integral, but nonetheless, you can't detect anything wrong with them at the level of looking at their asymptotic inner product. There's no issue with them. But yeah, when you look at the de Sitter S matrix, you find that they're projected out. I think that's where the tension is.
As Fox states, you can't put them together because you put too much of them together, you have too much energy and they crunch. So that would be one problem for example. But you could just decide to restrict yourself permanently to that part that sails through, and then.
Well, yeah, I mean, I should say there's not really a notion of Fox. Well,
I know.
Yeah.
But yeah.
Yeah, I mean, yeah. Okay, so the thing I just wanted to say was that, I mean, right, I just mean that more broadly, okay, good. So I want to remark on one thing that you said, which was that this S matrix is a very trivial kind of object. Its eigenvalues are 1 or 0, projects you or it kills you. Now, the reason why it ends up being all 1 is that that ends up being tied to the fact that in this very simple model, the bulk evolution of the asymptotic states is just trivial on account of it's just nothing happens to you. So if you live, nothing can happen to you, sort of to be kind of by consistency with what happens in the bulk, but otherwise you get projected out. So that's just wanted to draw a bridge between those two thoughts.
Could you just say a word on the computation that gives your I over phi minus phi prime plus I epsilon?
In the matrix model or in general?
Gravity.
In the gravity case. So the I epsilon, okay, so there's different features of the computation, but essentially you can do a computation of each of the trumpets. And when you glue them together, you have to, and you integrate over alpha squared, you have to, the I epsilon is included so that moduli space integral, so the integral over alpha squared converges. So there's an integral over alpha squared. In order to get it to converge, that is where the I epsilon comes from. I'm not sure which feature I should remark on in particular, but if it was about the I epsilon, it is put in there so that integral converges.
I'm still wondering about the fact that phi was allowed to have both signs. Phi was on the real line.
Yeah, let me comment on that later because I omitted part of the formula, so let me not attempt to do that in real time. But it can take both signs. The formula that I wrote down was a bit deceptive.
Well, the formula you started with gave a classical solution for either sign of phi.
That's right.
But there was strong coupling in the far past and future. Or actually, sorry. Since phi is proportional to sinh, didn't you always have strong coupling in the past or future?
Yeah. Yes. Well,
it was small phi that was proportional to sinh, right?
Yeah. So, sorry. So there's two different. So the boundary conditions on phi. I mean, let me maybe write it. Let me write it in a way that the exponentiation is the thing which confuses the issue of the sign. You don't actually have to parameterize it in that way. Let me write it in a slightly different way if you prefer. Is that the asymptotic boundary conditions again? So for the metric, it's e to the 2t, or sorry, it's minus et squared plus e to the 2t plus subleading times dx squared, and then for the dilaton, it's it goes like e to the t times. Let me not write it in exponential because that's sort of where the issue comes in. Times 5x plus subleading. That's a better way of thinking about it. Not to write this as an exponential.
But your discussion where you were saying that phi is positive and so on, it's tantamount to saying that this coefficient is positive.
That's right.
So I think that the solution that you had in the beginning, right, will not describe the transition amplitude. The transition amplitude would be something where the dilaton is growing both in the past and the future. Right? And it's a configuration where phi is not the solution inside.
Where phi.
Yeah, it's like as in the Euclidean trumpet, the trumpet solution where phi is some solution. There is no classical solution for phi.
Right.
Integrate the Rothschild configurations.
Yes. No, that's true. No, I was just saying Right, but there's that is true. I was saying the separate fact for Josephine's question was just this issue of, there was just this issue of parameterizing phi in terms of an exponential because it made some formulas nicer, but it obscured the fact that this thing is really just a function of x that can be positive or negative.
But if it has the wrong sign, for
Yeah.
example, negative, or in strong coupling, we might think the model doesn't make much sense. So for that reason, you might want to restrict to positive values.
Well, so certainly if you look at the model as like a dimensional reduction of, so these unitary geometries where you look at just these one-sided, you just look at states that have a single, like a future region, it is completely natural and in fact compulsory to make phi positive. So it corresponds to some radius or some positive parameter. But I don't see why, at least in the JT model in and of itself, not coupled to anything else, what obligates us not to allow phi to be negative in the far past or negative in the far future. It's just about
Just the topological corrections would be very, very large if phi is the wrong sign. And we might think that that's some kind of strong coupling. We might feel that you're just giving us a semi-classical picture. That's good when those corrections are not too big. But when phi is very large with the wrong sign, we'd be out of that region.
Yes. Well, so there's a question also of how to treat what the higher genus or what those corrections look like and how to compute them.
There is such a question, but we would think that they shouldn't have a large negative action.
Well, how do I say? Yeah, I don't have anything to say at the moment about the higher genus case, but yes, but fair enough.
So if you restrict it to positive phi, would you also restrict P? Right?
Well, they're related by a Fourier transform, so it would just change, you would have to put a step function, but anyway, it would change the analysis.
Can you remind us what's real and what's imaginary? The starting point with JD gravity, you had phi times the curvature, etc. Is phi real or imaginary there?
Real.
Real. So that's, and it's integrated between minus infinity and plus infinity?
Well, the discussion was whether phi should be allowed to be negative or, be allowed to be negative.
But you started with an action in Euclidean space, which was had phi times r minus 2 or whatever.
Yes.
Is phi real there or imaginary?
Phi is real. But it's in signatures. There's an I in front of everything. It's e to the I action because it's Lorentzian. Phi itself is real.
I see. So I shouldn't think of this as a Euclidean pattern.
No.
Except when you discuss the Harle-Hawking state, I suppose.
Yes, that's right. Except in the Harle-Hawking state when you prepare the cap.
I have another question. The Harle-Hawking state, does it satisfy the physical states condition or not?
Yes, it does.
It does?
I believe so, yes.
In ordinary string theory, viewed as two-dimensional gravity, it doesn't.
Perhaps I have the wrong understanding, but I see no issue, at least at the level of these analyses, when you account for diffeomorphisms in the usual way. I don't see any issue in this analysis with the Harle-Hawking state, so maybe I don't.
Maybe I'm worried about the higher genus corrections.
What were you asking?
Whether you're worried about the higher genus corrections.
No, I'm already worried in the sphere.
Yeah, I'm not sure I'm not sure how to address that. I'm not sure how to address that connection that you have in mind too in the stringy context.
I don't remember all the details, but we wrote a paper with Jorrit where we studied the weird equation in the context of JT gravity and solving it, and we were getting answers consistent with the way people compute partition functions with instruction.
Okay.
Yeah.
I mean, naively, the Wheeler-DeWitt equation just says that the wave function is a function of what I think you call P.
Yeah.
And the Harle-Hawking state was an example, so
Right.
it satisfies the Wheeler-DeWitt equation. Well, assuming that formula for the Harle-Hawking state is correct.
Yes. Well. Yes. Well, several. Well, how do I say? The formula for the Harle-Hawking state used was one that was independently derived, I think, by several people in the room. The new ingredient was evolving it back to the cap using V dagger. That was the new ingredient. This delta prime of P minus 1 was, that's a new formula, but it's gotten by taking the formula, which is one that many different people have computed and agree upon, but then kind of evolving that backwards with the trumpet, with V dagger.
Can I ask explicitly what example in string theory you had in mind where it doesn't solve the Wheeler-DeWitt equation? Okay.
Nati, what did you have in mind? What was what was your
think of string theory. It is all based on intuition from some 30 years ago, so I might not remember well. But if you think of the wall sheet as 2D gravity, and you try to imitate what we do in string theory, then roughly speaking, the Harle-Hawking state is the identity operator, which is not a physical state. And you can see that if you just analyze the states in, say, in the metrics model or in Liouville gravity. And it's associated with issues that are similar to what you said. In order to implement the Wheeler-DeWitt equation, that corresponds to integrating a component of the metric, and you need to get a delta function, you have to integrate it between minus infinity and plus infinity, rather than from 0 to infinity. And the prescription being used in string theory is to integrate from 0 to infinity. So the whole issue of the Wheeler-DeWitt equation is more subtle. And it's not unrelated to what you said. It's of whether the size of the neck is positive or can also be negative.
I see.
I think Greg is still, if Greg is still there, he might remember more than me.
I don't think he is.
Okay, if there are no more questions, let's start them again.